It's so hot in here.
It's not that hot.
You have AC?
Yes, I have AC.
It's not even on.
Okay, so we have questions on the homework. You guys are saying. Okay, let me erase this
Oh
stuff.
my gosh, those are easy. There's only one.
Okay.
Use like find
What did I do wrong? It was homework?
Are you guys worried about your grade?
Yes.
a little bit.
No.
Okay, there you go. Whoever said no will get a B. Everybody else C.
Was homework MVC
Nice.
1?
What?
Was homework?
No, homework is 16.4. We're doing it for the book now.
We are. Sorry. Oh,
There's no worksheets for quadratic surfaces,
Yeah.
right?
Because it's find derivative.
Oh, I thought we had
They're all
zeros.
constants.
Because you taught us yesterday.
Yep.
Hey, where did that come from?
Oh, website.
Oh, but that's the same thing. That's the same thing as the star problem.
I was testing you.
So yeah, I guess so. For real, I didn't even know we had that.
Okay.
I had that.
Oh, shit.
Okay, which problems are you doing?
17.
Gosh, for real, my knees are sore just from doing 3 classes already.
4C.
Can you do
15,
17, and 21D?
Okay, from what's the first number?
15.
15.
Jason Cho, what section are you on?
He printed out like a worksheet or something.
I didn't get
I
one.
don't even know where that was. Okay, let me tell you this. Whenever the book has log, that actually means natural log now.
Oh my god, are you serious?
Yeah. That's the way, I don't know why they did it, but that's the way they did
Well,
it.
that explains a lot.
Okay.
Still is confused.
So, compute the partial derivative of f with respect to x at 0e, and then the partial derivative of y at the point 0e. So, let's compute the partial derivative of x. Okay, who's got this one? Ha.
Wait, it's e to the x, but e to the z.
Huh?
E to the z natural log y, right? Or did I
Wait,
copy
E
it
to
wrong?
the x.
Oh, e to the x. And wait, this problem is pretty easy. Okay, ha?
E to the x.
Thirty.
L, y. Oh wait, no.
Times what? Remember,
It's over-
y is a constant now, yeah?
L and y. No, no, no.
Yeah, so L and y.
Oh, why can't I remember that was wrong?
Because that's a constant, you throw it on the side like an
That's what I
unwanted cat. Okay, partial derivative of f with respect to y now.
E to the x, 1 over y.
Over y.
Over y.
Okay, so all you have to do now to compute these is plug in the numbers. If I plug in 0 for x and e for y, you get 1 times 1, 1. If I plug in 0 for x and e for y, you get 1 over e. What can,
Oh,
that's
no.
nonsense.
I thought, I got them.
I didn't know the log.
Oh, you didn't know the log. Okay,
You don't have to do
17.
Okay, never mind.
no need to do 17 then.
No, can
Wait,
you
what?
Just do
I
it.
can
Wait, 17 doesn't have logs.
No, but no, I just couldn't get it. I got negative 1 and
Okay,
0.
G. Oh, you know why they confused you? Because all the problems are F and now they suddenly use a G.
Yeah,
I hope not.
that's what
Side.
happened.
X plus 2y. Compute a partial derivative of G with respect to x and y at the points. Okay, so
Can you just do x? Because I got y, but I couldn't
okay,
get
G partial derivative of G at 0 pi over 4. Okay, what's the partial with respect to x? Okay, Park.
that. Negative 1, negative e to the negative x. Cosine.
No. It's a
Oh,
product.
sine,
you
sine,
gotta use
yeah,
the
sine
product
x,
rule.
sine x.
Derivative of the first, leave the second one alone.
plus
Leave the first one alone. And what's the derivative of the second one?
cosine x plus 2y.
Cosine x plus 2y times
You didn't. Oh,
the derivative of box.
1.
1.
Yeah,
Okay, then
I got that.
all you have to do now is plug in 0 and pi over 4.
It's right here.
Negative e to the 0. I'm just gonna put negative 1. Okay, sine of 0 plus pi over 2, that's 1. Plus e to the 0 is 1. Cosine of 0 plus pi over 2 is 0.
Yeah.
So negative 1.
No, but the answer said 0.
Yeah, the book is wrong then.
Oh, yeah.
Really?
Zero.
Yeah.
Okay, that's the correct answer.
Okay.
Wait, did you get 0 for GY?
Yeah, I got you. Yeah, I got 0.
Okay,
So the answer was
it
not
wrong
even
for-
close then.
It was wrong for both then, yeah.
Wait, what? No, I think you
Let's check
I
the
said
book.
it was
Maybe I just started by both of them. Never mind. If you got 0, then the answer is 0.
Yeah,
Alright, okay, what's the next one?
21.
21C.
Okay, I gotta scroll.
Just bear with me.
What is
Okay.
21?
I just need
What
to
is
try.
21C harder?
You just plug it in.
I
They
know
give you
like
numbers and you just plug it in.
no, I was like A B C D E. No, not doing it.
It's because there's.
Okay, before we do
Yeah.
21, I was thinking about it when I was driving to school today. Like, what do these partial derivatives mean? Remember how, like, when you take the partial with respect to x, keeping y constant? So remember, there's a picture in the book. Like, if you have a surface, oh gosh, I can't even draw these three. See, you have a surface, that's bad. Okay, so if y is constant, that means like a plane, like y equal 2. In the plane y equal 2, so like you have a surface. If you intersect it with the plane y equal 2, you might get something that looks like that, yeah? That gives you the rate at which the function is changing with respect to x, keeping y constant. So it's like the slope of the graph in that plane, like y equal 2, y equal 1, y equal 0. But here's another way to think about it. Maybe this way is better. Suppose you have a surface, okay, let's say you have a contour plot of that, like, you guys know what a contour plot is? Like,
Yeah.
okay, think of this as like a mountain. So like this is the highest part of the mountain, and then if you go like
Yeah.
down 1 meter, then it looks like that. Then you go down another meter, it looks like that, yeah? So the mountain is going up like that.
Level curve?
Yeah, level curves. You can think of it that way. Okay, so let's say, okay, here is x and here is y. So let's say you're standing somewhere on this mountain. Let's say you're standing right over here. Okay? So if you look that way in the positive x direction, that's the partial with respect to x. How the function is changing. Like, so you're standing on the mountain. Okay, like I'm on the mountain. And I look in this direction. Like, what is the slope right at that point there in the x direction? So if you're standing on the mountain and you're going down here, isn't the mountain going downward like that? So that's the slope right at that point. You know what I'm talking about?
Yeah.
Okay, and then what now if you face in the y direction like that, you look that way. Now you're going to be looking up the mountain, right? So this is the slope or the partial with respect to y. So right at that point, what is the slope of the mountain? Right at that point, you're looking upward like this now, right?
So that, the slope with respect to y would not have an x.
No, because it's in the y direction only, yeah?
So it would only
So
have
the
y.
partial with respect to y is either you're looking that way or that way, right? Because of course if you're looking this way, then you're looking up the mountain, right? The slope is going that way. But if you're looking down the mountain, then the slope is going that way. Yeah? But then if you're looking that way, the mountain, you know, if the mountain is like this and you're on the slope, you don't know, right? I mean, could be like, could be something this way. And then if you look that way,
You don't know.
yeah, you don't know. Could go up a little, could go down, could be just flat, right?
It's ambiguous.
Okay, so that's what these partial derivatives tell you. Okay? But next chapter, we're going to learn this thing called the directional derivative. See, this one just gives you the slope if you look in the x direction or the y direction. What if you look in any direction? Like, what if you look in that direction? What's the slope? So so we're going to learn that next chapter. It's called the directional derivative. It can be in any direction. Not just in the x or the y direction, any direction. So actually these are simpler because you're just looking at the slope only in the x and the y direction. Okay, now let's do 21.
Oh, you just have to find your numbers.
Yeah. No, I don't know how to do D.
Okay, 21. The area of a triangle. Come on! This is an insult. We learned this in trigonometry.
You use the formula.
So suppose that b is 10, c is 20, and a is pi over 3. I have to compute the area of this triangle.
Yes, please.
You know what, I think okay, so the area, and I hope you know that this is not a K, right? That's the Greek letter kappa, that usually represents area in mathematics.
Cap.
No, for real. In mathematics, they like to use Greek letters. Alpha,
Yes.
beta, gamma, delta, epsilon.
B.
Kappa.
I'm
No.
trying to remember the Greek alphabet. Wait,
Okay.
alpha, beta, gamma,
Micro.
delta, epsilon.
B.
I think it is omega.
The last one, the ending part of the alphabet is phi, C,
Oh,
Ki, Omega.
What's the one that looks like a weird
Oh,
sig?
what's the
The one that-
Sigma. Sigma, Tau, Upsilon. I don't know how to graph. I don't know what Upsilon looks like.
What's
That's the Greek letter for you though.
Upsilon.
What? Mu, Mu,
Is there twins?
Nu, Z, Omicron, Pi, Rho,
Pi's in there?
Sigma,
Wait, what is
Theta, Theta, Tau. See, Tau is the Greek letter for T, but Theta is the Greek letter for TH.
So there's,
It's
how many
like
letters are there?
I think there's 24 letters in the Greek alphabet.
Is ohm one of the
Ohm.
letters? Yeah, like,
OHM.
you know, like the ohms?
Oh, like that thing.
Yeah,
That's
Oh, that looks like
Looks like old.
physics.
yeah, it is physics.
Oh yeah, that's pretty.
I'm not sure. I gotta brush up on my Greek alphabet. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta. Zeta, eta, theta!
Zeta, eta. Let's look.
I don't know what zeta looks like. Some zeta, eta,
Alpha, beta, gamma.
theta,
Epsilon.
mu, nu, C, omicron,
What's
whatever.
iota?
Oh, iota is I. Iota.
Kappa, lambda.
Kappa, lambda,
Mu.
wait, lambda,
Mu.
mu. But I don't know what mu looks like. But
No. I thought
It's like a weird.
yeah.
it's like-
Oh, mu.
Yeah.
Yeah.
Mu,
Nu.
nu.
C. Or
No, that's not nu. It is nu.
XI. What's XI? C.
Z. Okay, whatever.
You're the
You-
one. Omicron.
They like to use, and then these are the lowercase Greek letters, like like sigma, and then uppercase sigma looks like this, yeah.
Oh right. The sun.
And then pi, lowercase pi, uppercase pi. Why is that funny? I don't know.
What
Okay,
is Omicron?
Omicron, the Greek letter for O. I don't know what it looks like. Is it like that?
No, it's just this O.
Okay, Mr. White, let's just.
Omicron.
Yeah, it's right here.
Mr. White, let's go back to the topic.
Okay, let's go. Oh, you guys brought it up. You guys said, what is this K thing? And I said, it's not K, it's kappa.
We didn't say what
Well, I was thinking that in my head. Okay, 1/2 BC sine of pi over 3 is, what am I even writing
Wait, you
this down?
forgot 20.
Yeah, 20. Sine of pi over 3 is root 3 over 2. So 4 goes into 20 5 times, so 50 root 3. Come on, that's an insult. B, find the rate of change of the area with respect to the side B if C and A remain constant. Well, you don't even have to say that. If you say with respect to side B, then you just assumed already. So, the kappa, the partial, what's the symbol for partial? Let's just do kappa with respect to B is keeping everything else constant.
1/2.
So everything else is constant, that's the only variable, the derivative of B is 1, so it's just 1/2 C sine A, right?
Oh yeah.
Okay.
So easy.
Part C. Find the rate of change of the area with respect to the angle A if B and C remain constant. So that's your variable, everything else is constant, so kappa with respect to A is 1/2 BC is a constant, and the derivative of sine A is simply cosine A. And then D, using the rate found,
Oh yeah.
no, we got, wait, did we do A, B, and C? Already.
You did look
Oh, we did. What? D, using the rate found in C, calculate by differentials the approximate change in area if the angle is increased by 1 degree.
Yeah, how do you go with
it. Yeah, I don't know how you make
Okay, let's go back to BC calculus. Let's say you have a function like this, y equals x squared. What is dy dx, the derivative?
Hey, y equals x squared.
I'm thinking ahead, sorry. If y equals x squared, what's the derivative? See, that's the thing when you get old. You think one step ahead and then all hell breaks loose. Okay, so the graph looks like this, right?
Yeah.
So we can approximate the change in y. Does this sound familiar with like Euler's method?
It's dy dx times change in x, right?
Okay, so dy dx, oh, very good, Park, times delta x.
Thank you.
So we can approximate the change in y. Okay, so let's say x goes from, what shall we do?
0 to 1.
0.
No, 1 to 1.2.
Okay.
1, so from 1 from x equals 1 to x equals 1.2. Approximate the change in y. Of course, we can actually compute the actual change in y, right? The actual change in y is the y coordinate here, which is 1.2 squared, minus, what is the y coordinate there? 1 squared. That's the actual change in y. But then for more complicated functions, it's not going to be that easy. So we want to be able to estimate it, okay, by using this. Okay, so the approximate change in y is dy dx, which is the derivative, 2 times x, which is the slope, times the change in x. Why am I putting that? 2x, and what is the change in x if it goes from 1 to 1.2? 0.2. Now, what do I plug in? What do I plug in for x? Where did I compute the slope of the tangent line?
1.
At 1. So you plug in 1 for x, and what do you get there? What is 2 times 0.2? 0.4. So the approximate change in y will be about 0.4. Compare that to the actual. What is 1.2 squared? 1.44 minus 1. 0.44 is the actual change in y. That's pretty darn close. Because that's based on the tangent line, yeah? So if you have the tangent line here, if I go 0.2 to the right, how much am I going to go up over there? Can you see that it's kind of very close to each other? Remember linearization?
Yeah.
Oh.
Wait, what am I talking about? The change in y and the actual change in y should be the same. Yeah, forget that other point there. Okay, so let's do this problem, D. Using the rate found in part C, calculate the approximate change in area if the angle is decreased by 1 degree. So the change in area is approximately what? If we use what we did there?
1/2
The derivative,
of
which is this right here, the 1/2 BC cosine A times the change in x.
which is a
No, not the change in x, change in A. What is the change in A?
1.
1 degree.
Increased by 1 degree, so we got to convert that to radians.
Yeah.
1 degree, how do you just pi over
Oh
180?
my god.
Yeah.
Pi over 180. Okay, so what do I plug in for B? 10. What do I plug in for C? 20. What do I plug in for A? Pi over 3. So the approximate change in area will be 1/2 times 10 times 20 cosine, that's 1/2 times pi over 180. Can I do any canceling? 4 goes into 25 times, 10 goes into 118, so 5 pi over 18 is the approximate change in area. What does that come out to? What is 5 times pi? 15.7 divided by 18. What is 15 over 18? 560. Point. Here's my guess. 0.85.
It just says 5 pi over 18.
Oh. Who has a calculator? Huh?
I don't have
Okay, I have my phone.
a.
Oh my
Look,
god.
even a phone like this can compute.
Really? It
Yeah.
says pi?
No, but I know what pi is.
Oh.
Okay, calculator. 5. I can't even see the buttons. Times 3. Where's the decimal point? 0.14159. That's probably good enough, yeah. Divided by, where's the divide side? Divided by 18 equal 0.87. Darn it, I was off.
Let
I
me
said
try.
0.85, but it's
That's
actually
fine.
0.87, yeah.
Is that change in area or
Yeah, the approximate change in area.
Can you, okay, so it's not the angle, right? The change in A because
No, they're saying if you increase the angle by 1 degree,
yeah.
so like you have a triangle like this. So right now the angle is pi over 360 degrees. If I increase this angle to 61 degrees, by how much would the area approximately change?
No, I was just confused because you wrote it's A for the degree and you also represented A as an area.
Oh, sorry. Okay. Change in area. Sorry. Okay, and then what about part E? Find the rate of change of C with respect to B. Whoa! So that means, now what do you want to do? You want to manipulate the equation and solve for c? I think that would be the easiest way. So taking the equation and solving for c, solve for c, what do you get? 2 kappa over b sine a. If you solve for c. Did I do that correctly?
Yes.
Okay, now take the partial with respect to
B.
b. So what is the partial of c with respect to b? Everything else is constant. So this is a constant, so 2 kappa over sine a, and then just multiply that by the derivative of 1 over b. What's the derivative of 1 over b?
Negative.
Negative 1 over b squared. Boom. There's the answer. Was the answer in the back? Did it say this? I'm pretty sure it did. Okay, and remember last week I told you what's the other way of writing partials? Like if you have z equals x squared plus x cubed, y cubed, so let's do something simple. What is the partial of z with respect to x? That's the way we write it. It's kind of like dz over dx, but then when you're in multivariable, we use this symbol. I'm pretty sure it's a Greek letter. You have the Greek letters again? Was there one that looked like that?
Probably.
Okay.
I don't have it written.
Okay, so what is the partial of z with respect to x? The answer is 2x. What's the partial of z with respect to y? 3y squared. But you got to get used to this other notation as well, because today we're going to do second derivatives.
No.
Okay,
I was just gonna ask if you can just put it like k sub b, or like k sub a.
yeah, but then what happens when you get to the second derivative?
K and then like prime.
Yeah, but how do you, okay, but when you put a prime, what variable are you taking the derivative with respect to?
I'm gonna say k prime b.
Oh, no, so that's why we want to stick to the official mathematical notation. Okay, I'm going to take a problem right out of the book then. Okay, today's lesson is super fast.
Okay.
Because if you can take a first derivative, come on, you can take a second derivative. So if you look at tonight's homework, you just got to get used to the. This test is pretty easy. Probably the hardest part, my guess, is going to be the quadric surfaces part. This partial derivative stuff is easy. Okay, let me look at it going, oh there! I like that one, number 4. Number 4. So we have a function of x and y, which is, oh, you can think of that as z if you want to. X squared cosine y plus, I'm going to put y cubed sine y, sine x. So let's do, what is the partial of f with respect to x first of all? Cho, this is like last night's homework.
2x cosine 3y plus
What?
cosine y cubed.
Wait, start all over again. Partial of f with respect to x, so 2x,
Cosine 3y.
how come 3y?
I mean, some 5y.
No, just y, that's cosine y.
Oh, okay, cosine. Y.
Plus
Y squared cosine x.
y cubed
I mean, yeah.
cosine
y cubed
x. Okay, did everybody agree with that?
Yeah.
Okay, what is the partial of f with respect to y? Ha.
X squared negative sine y.
Uh-huh.
3y squared sine x.
Yep, that's easy. Okay, but now what about the second partial? Okay, now watch. What is the second partial of f with respect to x? That's the way we write it. Kind of, doesn't that look like the second derivative, Leibniz's form of the derivative we learned last year? Look, d2y over dx squared. But since we're doing partial derivatives, we use that symbol. I gotta figure out what that symbol is. That looks like a Greek letter to me. So what you do is you simply take the derivative of this with respect to x again. Wang.
2 cosine y.
Mm-hmm.
Negative y to the third sine.
Exactly. what is the second partial of f with respect to y? So what you're gonna do is you're gonna take this and take it with respect to y again, Park.
Negative x squared cosine y plus 6y sine x.
And that's easy enough, okay, but then what about this? What is the second partial of f? What the heck is that? So you take it with respect to x first, but then you take it with respect to y second. Now, did I get the order correct? Gosh, I haven't done this in years. Wait, it's in the notes. Which one comes first? The mixed partial.
The y?
I didn't even see it. Oh, yeah, I found it.
Oh, you do the one on the right first. Oh. See, I almost blew it. So when you do this, you take the derivative with respect to y first, then you take it with respect to x. Okay, so we already did with respect to y first, that's this one right here, right? Right? This one right here, we took it with respect to y. Now take the derivative of this one with respect to x. Cho, what's the derivative of this with respect to x?
Negative 2x sine y plus 3y squared cosine x.
Yup, 3y squared cosine x. That is correct. Everybody see that? Okay, but now let's do the second partial of f first with respect to x and then with respect to y. Okay, now we already did it with respect to x first, right here. Now take this one and take it with respect to y. Huh?
Negative 2x sine y.
Negative 2x sine y.
3y squared cosine.
That is
That's the
correct.
same thing.
And then what do you notice about the two?
It's the same.
It's the same. So when you take this, they call this the mixed partial. It doesn't matter if you do it with respect to x first or with respect to y, it's going to come out to the same thing. But that kind of makes sense, yeah?
Wait, so the right side is what you've already done? Or
See that again?
on
Yeah, this one. You took it with respect to y first, that was this one,
So
yeah?
use that one.
And then you take this one and take it with respect to x.
Doesn't even matter though.
Doesn't matter, because these are always going to be equal.
Unless you did it.
In fact, if you look at the book, it says the equality of the mixed partial. Where is it? Hey. There. Equality of the mixed partial. They really don't say much about it. Whatever, they're equal. So it doesn't matter which one you do first.
But then it wouldn't be equal if you did a third.
Yeah, if you had to do a third one, ooh, that gives me an idea for a problem.
No.
Why not? If you can do one, you can do two. If you can do two, you can do three. Okay, so tonight's homework's super easy, super easy. All you gotta do is take partial derivatives. So, like I said, that part of the test is it's easy because it's very mechanical. It's the other part, the quadric surfaces. All right, we are done. You have 23 minutes remaining. Shall we use our time wisely?